So yeah, today we're very happy to have my a colleague, Qimiao Si, giving a talk. I mean, Qimiao has been known to the community for doing many, stuff on quantum spin. I mean, yeah, on quantum criticality. So today he's going to actually change this topic, talk about strange metal and flat bands. So I'll leave it to you, Qimiao. Yeah, thank you.
Thank you, Panchen, for the invitation. Right, so it's about strange metals and flat bands. What I wanted to do is really to make the point that the interplay between correlations and topology can be a two-way street, and use the heavy fermions and recently discovered superconductivity of twisted transition metal dichalcogenides as two settings to make a point. So let's see, my pointer was working for punching, but I'll use this. In many ways, strange metals represent the extreme form of colloid metals. One could make the analogy that when the interactions become strong in commensurate fillings in lattice settings, it's well known that multi-localization can happen, but even when the system stays metallic, there's some extreme effect of correlations. The most famous one that has been known the longest is the T-linear resistivity, but there's been increasing recognition that there's a slew of other properties such as dynamical scaling, Fermi surface reconstruction, loss of quasiparticles, and enhanced entropy among them as part of the characteristics of strange metallicity. And I'll come back to some of these. So to put this in a context, consider generic interacting lattice fermion systems. We have a band structure that leads to a Fermi surface, and the Coulomb interactions in the historical setting of treating many-body physics. One would do perturbation theory of interactions, or dimensionless parameter being interaction to say the bandwidth of the conduction electrons. And if one does a perturbation theory, the quasiparticles are resilient, and so this says that to infinite orders of the perturbation theory, quasiparticles persist, meaning that if one has say plotting the single particle spectral function, the width of this peak is for fixed k as a function of energy. The width of this peak is smaller than the energy, the peak location measured with respect to the Fermi energy. So if one could look at it in a number of different ways, but for example, if one looks at a bare electron excitation, there's a fraction of it measured by Z that lives in this coherent quasiparticle, coherent propagating quasiparticles, and the rest of spectral weight, 1 minus Z, would go to the incoherent part in some form. Now, so the question is, how could this robustness to the infinite orders of perturbation theory can break down? If interaction becomes large, if U becomes comparable or larger than D, actual things could happen beyond the realm of perturbation theory. So I want to narrow down to two particular contexts. One is heavy fermion rare earth-based actinide or materials, for example, in which the interactions are certainly larger than the kinetic energy of the F electrons alone. They could be smaller than the kinetic energy of these SPD electrons. So the F electrons act in low energies as spins, and they are part of the building blocks for low energy physics. In a way, one could also say that the F electron band being narrow by itself represents atomic form of flat bands. And the second context that has been studied in more recent years in this context of flat bands, beyond the prominent case of moiré systems, is something like Kagami metal, if the chemical potential is sufficiently close to the flat bands, then the flat bands become active. The flat bands here are formed not by atomic physics per se, but by the destructive interference enabled by, say, the frustrated nature, geometrical frustration of the lattice. And this leads to actual regimes of interaction physics by just looking at the hierarchy of the bandwidth. If the flat band width is much smaller than the wide bandwidth in the kinetic part, then I have at least 3 regimes of interactions as opposed to be 2. The Coulomb interaction could be comparable to the flat bandwidth. And that would, and if the chemical potential is sitting in the middle of it, that will lead to all sorts of electronic order due to the enhanced density states. But one could, in principle, restrict the analysis just to having one flat band with interactions in it. And if a Coulomb interaction is comparable or larger than wide bandwidth, one goes back to the atomic orbitals, the usual Mott type of physics. But if there's a hierarchy of the kinetic energy, it opens up a new regime of correlations where the Coulomb interaction is large compared to the flat bandwidth, or including the gap, separating that with the wide bands, but is small compared to wide bandwidth. So that's another context where there's in principle, it's a new regime of correlations, and there's bound to be new physics. So I want to come back to that. So just setting the stage for these 2 kind of regimes. And so that leads me to the outline of this talk. I want to use the context of heavy fermions to make the point that the band topology and the strange metallicity or aspects of strange metallicity can combine to be used to generate new forms of topology, and in this particular case, metallic topology, topological semimetals. And the other side of the interplay is that topology could enable new correlation physics. And I want to argue for this newly discovered superconductivity in the moiré transition metal dichalcogenides as a setting for, as a particularly transparent setting for illustrating this point, actually. So let me start from the first bullet. And to go to where I want to go with this topic, let me just make a reminder that interactions can create a new form of topology is fairly well established, extremely well established in insulating cases, such as going from the band topology of integer quantum Hall effect to the topology that only exists in the presence of interactions, that's as exemplified by the case of fractional quantum Hall effect. And the latest version of that in the form of fractional Chern insulators is very much the current the active topic. What I want to focus on in this talk is the case of is the metallic case, where you depending on the filling, etc., you could the system could open a gap, but symmetry prevents the gaps from being open, and that leads to Weyl semimetals or Dirac semimetals and related topological states that have been tested and realized in weakly correlated systems such as tantalum arsenide. So one could, and I want to ask that question, in this kind of gapless case, are there topological states that's driven by strong correlations? In some sense, the analogy of the question of the issue of going from integer quantum Hall to fractional quantum Hall, but now in the metallic settings. So to get to where I want to briefly summarize 2 aspects which will be coming together. One is the Weyl-Kondo semimetal. So this is the direction that takes advantage of the strong correlations in the form of the Kondo effect. Kondo lattice has been used to study correlation physics from fermi-liquid to non-fermi-liquid over a substantial period of time of the history of correlation physics. So you have local moments, which I already mentioned, came from the F electrons. They have the spin Hamiltonian describing the spin physics. Conduction electrons grew together by the antiferromagnetic Kondo coupling. And in the Kondo singlet state, which is illustrated here by the ground state forming the Kondo singlet, which could be considered as a bound state of local moment, and the particle-Hall combinations of conduction electrons. This kind of bound state formation in the ground state leads to excitations that includes this blob that has the local moment in combination of the electron or hole. So that's the composite heavy quasiparticle. One could think of this as a three-particle bound state from electron perspective. So for people who are in the semiconductor context, studying excitons, for example, this is essentially like a trial, and it's very heavy, except due to the interaction effect. And also, it's very fragile in the sense that the quasiparticle weight that I talked about is, instead of being very close to 1, it's far away from 1. It's typically on the order of 10 to minus 3. So 1 minus 10 to minus 3 of this original F electron spectral weight is living in the incoherent parts. And so I'll take advantage of that. So, but first, let's stay at this fermi-liquid level. And instead of considering genetic lattice as has been studied in the Kondo lattice heavy fermion physics context, let's take the lattice seriously. So in 3D, say the simplest is the 3D analog graphene, which is a diamond lattice. Diamond lattice would have symmetry enforced Dirac nodes. If I break the inversion symmetry, which I have done in this model, there will be Weyl nodes. But for generic commensurate fitting, such as I've chosen here, which is 1 electron per site, the electron, it would have, in this particular case, without a Kondo effect, I have arranged the f orbital levels to be what's typically happens in heavy fermions, which is deeper below the chemical potential. So the f electron wants to go, the electron wants to go to the f orbital. And in this extreme case, the conduction electron bands are completely unoccupied, but illustrate genetic case that these symmetry induced topological nodes genetically sitting in a remote topological bands. There's no particular reason that they sit at the Fermi energy. However, now if I allow the Kondo effect to happen, it will generate the composite heavy quasiparticle. So this is interaction driven. These are low energy excitations. Z being 10 to minus 3 means that these excitations are bound to the immediate vicinity of the Fermi energy. And on top of that, so anything that's symmetry induced, such as topological nodes, would be happening now pinned to the vicinity of the Fermi energy. For this particular commensurate filling, the system naively would have been to form a Kondo insulator, but again, symmetry prevents the insulating gap from happening, and that in the end ends up with Weyl nodes. And so this is still quasiparticles, but symmetry dictates that there's a Weyl node formation, which has fairly extreme consequences. So these nodes, ideally, one would like to, by analogy with say, Weyl nodes of tensor-arsenides, one would like to probe with APES. APES does not really have a resolution to see that, but we can do the correlated version of APES, which is that linear dispersion would show up in the T cube specific heat versus temperature. And the prefactor, unlike the usual heavy fermion physics of Sommerfeld coefficient enhanced by 3 orders of magnitude, here the prefactor would be enhanced by 9 orders of magnitude compared to non-interacting case. And that's actually seen in the material series 3 bismuth for palladium-3 studied by the Vienna group of Silke Passion. And in addition, Berry curvature induced Hall effect turns out also to be extremely large, as characterized by the Hall angle of on the order gigantic number like 0.5, and that's in fact what's seen in this semi-metallic heavy fermions as well. So this is a heavy, highly renormalized fermiliquid with a twist through the cooperation of lattice symmetry and electron correlation in the form of the Kondo effect. And this cooperation can be taken advantage of. We can look at, say, instead of looking at the diamond lattice, some particular space groups, and using a database to identify cerium-based materials. So, for example, in this particular space group, we identify 142 of these. We use some intuition to screen down to smaller number. In the end, we want the semi-metal. We want to be strongly correlated and instead of good insulators, good metals, and then to check literature measurements in the literature to see whether they are indeed strongly correlated, whether they are indeed semi-metallic. That leads to, in the end, 3 candidate materials. It's a recipe that could be used for other, there are many other space groups, such as non-symmetric space groups to look at, 150 plus number of those in 3 dimensions. And some of these that we identify have received some experimental evidence for the existence of these nodal states. So I don't want to dwell too much upon it, but it's a cooperation between symmetry and interaction that could be put to good use even in materials discovery. So that's a brief outline of the Weyl-Kondo semi-metal work that's has taken place over the past few years. I want to briefly outline the quantum criticality in heavy fermion metals, the strange metal aspects to come together with the topology. And these are studied for somewhat a longer period of time, although in the history of heavy fermion physics in this field, it's still a relatively young subject. And the strange metallicity is exemplified by this kind of temperature control parameter phase diagram, ytterbium rhodium-2 silicon-2, this orange color portion of the phase diagrams, the 115 in this green portion of the phase diagram. They all happen in a quantum critical regime. They all have T-linear resistivity. And to realize T-linear resistivity in these extreme clean systems being perhaps among the stoichiometric magic, perhaps among the cleanest of the strange metals. One would need to go beyond the description that invokes anti-ferromagnetic fluctuations, because that leaves much of the Fermi surface intact. So the theoretical consideration that we and others have done is to invoke the critical destruction of the Kondo effect, which is characterized by this E-star scale collapse into zero from the parallel magnet side. And that goes to the same place where the symmetry breaking order, in this case, anti-ferromagnetic order, the neo transition line terminates in the zero temperature limit. So there's not only the fluctuations of the lambda order parameter, but there's also the destruction of the Kondo effect. And we've been studying this using an approach that incorporates the dynamical interplay between the RCQY interactions among the spins and the Kondo effect, with a scheme that is inspired by the dynamical mean field theory, but incorporates this dynamical interplay, and it is systematic, etc. And so this approach allows to study the fate of the Kondo effect of the local moment coupled to both the fermion path and being in the environment of the fluctuations induced by the RCQM interactions. And this both Fermi-Kondo model realizes a new fixed point, which one can see from some analytical renormalization group calculations and from numerical studies of the finite size spectrum to see that, for example, at this fixed point, the finite size spectrum cannot be described in terms of the quasiparticles, and Z has to go to 0. And in fact, this is an interacting fixed point, so that all the microscopic energy scales goes away. So there's no room for something like a kBt squared divided by bare EF scale of the Fermi liquid, because all the microscopic scales has gone away, except for the kBt that's left as the only energy scale for this kind of interacting fixed point. And this allowed us to understand the dynamics data. So this is the forum mostly for the spectroscopy community, and spectroscopy played a central role in motivating the studies of strange metallicity in heavy fermion metals. Early on, it showed that H bar omega scales with kBt and dynamical spin susceptibility has this H bar omega of the kBt scaling form with a fractional exponent, and having this Kondo destruction allows us to realize the new fixed point, or kBt is the only scale in the problem, and therefore H bar omega of kBt scaling, and as well as the exponent that's anomalous and fractional, and that is also initially motivated by experiment. And kBt being the only scale in the problem also is manifested in the charge sector, and I'm showing here the electrical resistivity, which has a scattering rate that has the dimension of energy, and it turns out to be linear in temperature. So dynamical scaling is here very much a part of the strange metallicity. A few other features that I want to just very quickly, this has been talked about for in the past, but one thing that happens is that if you have the Kondo singlet that's formed on the parallel magnet side, you have this composite heavy fermions which are generated in the excitation spectrum, so Fermi surface becomes large. Well, if the other side is Kondo destroyed, these heavy quasiparticles are absent, and the electron count the Fermi volume equals X, and there's a jump of Fermi surface that has been studied very extensively by Hall measurements and quantum oscillation measurements. And finally, one could ask, how could the quasiparticles, how could the Fermi surface jump across a continuous zero temperature phase transition? For that to happen, the quasiparticle weight has to go to 0 at the quantum critical point. And so there's a complete loss of quasiparticles on the entire Fermi surface. About 10 years ago, there's some degree of evidence based on the Wiedemann-Franz ratio measurement, thermal conductivity, forming ratio with electrical conductivity. There's evidence for about 10% level of violation, but the more decisive evidence came only recently through the short noise measurement done here in the collaboration between Rice and Vienna University of Technology. So I just want to mention one more thing before moving on to where I'm headed, and namely that these correlation physics could actually be usefully helped with understanding through some entanglement quantities. So we recently looked at what's called quantum Fisher information. It's like a device system using the beams of the say in this case neutrons, and ask what's the degree of entanglement. Very much like Bell's inequality, you can measure correlations between the photons to test using the bounds whether the pair of photons are entangled or not. Here it's a many-body system, and this quantum Fisher information turns out to be peaked in the quantum critical fan. This is still finite temperature calculation, but it's peaked very close to the quantum critical point. And in fact, by using the bounds of the entanglement content of this through this normalization, is that there's a multipartite entanglement that happens within the quantum critical fan, and one could qualitatively say that the Kondo screen phase has the entanglement between local moment spins and the conduction electron spins. One actually needs some other entanglement measure to detect that. And the Kondo destroy side has the picture of the two standing alone. This multipartite entanglement suggests that you have these blobs. The quantum critical state is such that there's a blobs of entanglement, and that provides some way of visualizing the excitation that goes beyond the quasi-particle picture. So for at least for the Rice people in the audience from Rice, there's a workshop next week here on this topic. So now I'm ready to put these two together and ask the question: how could this extreme form of correlation physics in the form of strange metallicity or loss of quasi-particles enrich the topology, in particular, in this case, gapless, the semi-metallic topology? And so this leads to the Weyl-Kondo semimetals without quasi-particles. The first thing we did was that if we can study single channel Kondo effect, which is what I described, we could also study a multi-channel Kondo effect and put them in some interesting lattice. Multi-channel Kondo effect has local moment not coupled just one species of conduction electrons, but in fact two degenerate species of conduction electrons. So local moment spin wants to form singlet with this species of conduction electrons, and at the same time it wants to form spin singlet with this species of conduction electrons through the antiferromagnetic Kondo coupling. The two things cannot happen simultaneously, so this frustrated situation in the two-channel case leads to non-fermi liquid, as would be, say, the three-channel and the multi-channel case. And so this is captured by the spectral function. It's like A omega K. It's like a theorist version of RPS measurement for each given K, spectral function versus omega. And so instead of sharp peaks, as one would see in the quasi-particle case, these are very broad peaks. But nonetheless, one can trace out the peak locations to see that I have two branches of excitations, which are not Fermi liquid because it's not sharp, but there's special K, a special value of wave vector at which the two spectral functions have to be on top of each other, or at least you can just pay attention to the peak location. They have to disperse and merge at the special K for symmetry reasons, and then they disperses away from each other again. And so this is the a non-Fermi liquid form of the Weyl node. And one could ask, how would one know? We can formulate a problem in terms of the eigenvectors of the Green's functions, and that serves as the analog of the block functions, and see that there's the corresponding Barry flux, for example, is quantized, and would have to lead to some will have consequences for the bulk boundary correspondence. And in fact, that's one way for us to probe the topology, which is to ask whether there are surface states, and that one would expect if the bulk state is topological. And we did a calculation for this model to show that there's indeed Fermi arc-like surface states. But again, if one probes the spectral properties of this Fermi arc states, they have non-Fermi liquid form, and based on the calculation of local correlation functions, it behaves similarly as the bulk excitations. It's in a form that's consistent with a fractionalization. The bulk for 2-channel would be fractionalized into Majorana fermions. 3-channel Kondo lattice would be fractionalized into parallel fermions. And in the for the surface states, we we observe very similar local correlation behavior as a function of temperature and frequency. And then finally, if there were topology, say barrier curvature, it would be manifested in various type of transports, such as Hall effects, spin Hall, Barry Hall, nonlinear Hall effects, and we did the calculations for those, and they are present, but they are distinct in that their temperature dependence feature the non-fermi-liquid form. So this this topological semi-metal realized in the 2-channel Kondo lattice, in some particular lattice, qualifies as a topological semi-metal without quasiparticles, and we did the related form of material search to propose that several candidate materials. Here, instead of cerium, ytterbium-based, came out to be praseodymium, uranium-based in order for the 2-channel to happen. So this is a 2-channel case. This is in some sense from where I started. It's a detour, but one could ask the question back to the 1-channel Kondo effect in this interesting lattice. Could we also tune the system to the quantum critical point? And so we studied the RKKY versus Kondo interplay in this 1-channel Kondo problem, reaching the quantum critical point, which is signified by scaling h bar omega of a KBT scaling, for example, in the spin dynamics, and in part also motivated by this material in which the neutral made by Silka Parshin's group, and the neutral scattering measurements of Colin Broholm a few years ago actually show that this semi-metal system has dynamical scaling in a form that's quite similar to what's observed in cerium copper 6 gold. And but back to the theoretical study, we again look at AK omega and see that the 2 branches of peaks that come together at this special K point where they come together. So that realized the interacting form of Weyl nodes, and then keep on moving to other Ks, it disperses away again. This is also seen here. This scan here, it would be the vertical scan here. So you can see that there are 2 branches that came together to this special K star point, and they go back away. And this is corresponds to a Weyl node with excitations that go beyond quasiparticles. So this is an example in which correlation through the breaking of the quasiparticles creates a new type of gapless topological states, topological semi-metals. And at this point, I want to come to the second part to illustrate what we believe to be an example in which topology, band topology in the present for system in the present of interactions enables the correlation physics. So superconductivity in twisted-WSe2, this is only 4 months old story, and in twisted graphene, superconductivity has been seen for quite a number of years. In moiré transition metal dichalcogenides, there has not been observation of superconductivity until, as I said, 4 months ago. So instead of graphene, one looks at, in this case, WSe2 with the lattice that's seen here. The single layer of WSe2 already breaks inversion symmetry. There's a strong spin orbit coupling that actually simplify the degrees freedoms. The valley and the spin turned out to be locked together, and one puts 2 layers of this, twist them, and forming the familiar moiré structure with the reduced Briançon-Moiré Brilliant zone. And the reaction happens here. And so genetically, there's a flat band. And one could realize something like a half filling of the flat band. And so if one has a flat band, certainly at the model level, flat bands were historically introduced to have enhanced density states to create electronic orders such as alternate ferromagnetism and other possible electronic orders. And in cousin materials like twisted-WSe2, this kind of electronic orders are in fact realized. There's ferromagnetic order, there's evidence for fractional churn insulators. And so interactions in flat bands at least at the if we want to look at the big picture view, it's very natural to cause order, and the band topology can make the order topological. So these are systems that have been very good setting for study these topological, say, fractional churn-like systems. So the supplies in the recent time, based on measurements of the Cornell group and the Columbia group, is that there's a superconductivity that's sitting near electronic order. So this is this red part of the displacement field, electron filling phase diagram. So it's close to nu equals to 1. It is represent some degree of electronic order. Maybe there's even localization. And in the extreme vicinity of it, that's where superconductivity is observed as resistivity versus temperature. And if you zoom out to a bigger phase diagram, so this is the superconductivity part of the phase diagram. These two blobs here are part of this half-filled, at least in the Cornell experiment, half-filled correlated phase. And there's a lot of discussion out of Van Hoff singularity, etc. At least by a certain way of tracing the Van Hoff singularity, the superconductivity is not happening in close vicinity. In fact, it's far away from it. Now, so that's the observation of superconductivity. That's exciting. But there's a slew of other features that make this this experimental observation to be, in my opinion, to be particularly exciting. So one is that the normal state is a better metal. If you look at the sheet resistance versus temperature at this half-filling case, nu equals 1, it reaches a value which tells us that KFL is of order unity. And so we have a bad metal there. And this kind of temperature dependence of resistivity is also interesting, defines a scale that could be considered as, based on experience, we say something like a heavy correlated materials like a heavy fermion. So if one can reach high enough temperature for the bad metals of Mott systems, presumably there are features like that as well. One could define that as a Fermi temperature. And in fact, by that measure, TC, even though the absolute value is not all that large, the ratio is a few %, and that's very much what one sees in heavy fermion superconductors and a variety of correlated superconductors. And finally, there's evidence for proximity to quantum criticality. This is through a practice that resembles what is done in heavy fermion superconductors. One looks at the Fermi liquid temperature dependence, T-square resistivity, and ask what the slope of this T-square resistivity is, and look at the A coefficient as a function of tuning parameter. In this case, it's tuning towards the superconducting region from the from this side. And one sees that this A coefficient is increasing by more than order of magnitude. And so that provides evidence that the effective mass is m star of m is increasing, the system is becoming soft, and very much like the phenomenology of heavy fermion, many heavy fermion superconductors. The direct evidence for things like T-linear resistivity, etc., for strange metal behavior is not actually that strong at all. But nonetheless, it suggests that in the part of the parameter space that has not been reached, there's in fact a quantum critical point, and superconductivity is happening not too far away from the quantum critical point. At least it allows that the hypothesis. So putting this, taking this phenomenology into consideration, but also putting this perspective that the flat band naturally breeds electronic order, we've looked at this problem from the perspective of analogy with something like cadmium metals with active flat bands, in which I already mentioned in the introduction that if you have two kinds of bandwidth with a hierarchy between them, you open up a window of interactions that's in between. And so now one could consider this destructive interference, taking that seriously, that would lead to something like a blob, a molecular orbital, except that's not a very good representation. It's not orthogonal to the ones coming from neighboring unit cells, and it's not even complete. But recent work has pursued this direction to show that if you combine taking these molecular orbitals seriously, one could go back to the subset of those flat and wide bands to form these molecular orbitals. Some of them are more compact than the others, and the compact one is in fact the descendant of this, in the sense that you can add decorations in the tails, in the spatial distribution, in such a way that this one and the one coming from neighboring unit cell would be orthogonal, are orthogonal to each other, and they represent a complete basis. So we've been pursuing this in materials like 135 based on chromium. That's a new material in the Kagame system that we've been working with Ming-Yi, Pen-Chin Dai, Rosa Valenti, and there was a talk by Ming a few weeks ago, which I think is available on the online, and presents a very rich phenomenology and interesting theoretical questions. So here I want to use that as a guide to think about the flat band in combination with nearby wide bands. In fact, if one does a reasonable estimate of interactions would be mixing the flat band with the adjacent wider bands. And it is not entirely clear. We know the bands are topological, but precisely this true number for particular value C equal to -1, whether it's accompanied by -1 or +1 for the nearby band, is depending on the choice of the moiré potentials. So we'll work in a regime where it's the C equals spin churn, the valley churn number having opposite from two bands in that regime, and it turns out that in this case one can construct these molecular orbitals. Some of them are closer to half filling, and the others are far away from half filling. So that provides a way to make the following general point: the band topology does not allow us to study the interaction effects, which is better to think in a real space way, in terms of certain real space orbital description. Instead, one has to consider real space orbitals coming from the combined bands, and the topology dictates like that there must be hybridization. So this is the analog of going back to the F-electron materials. Genetically, the F-electron materials provide a very good setting for hard magnets. So hard magnets would be the analog of this natural tendency of order. And in fact, there are many more rare earth-based and actinide-based materials which would be ordered, except that for our community, we don't pay particular attention to that. We, in fact, go to the part of parameter space where quantum chemistry dictates that there's hybridization. And then we say, the hybridization induced quantum fluctuations competes, leading to Kondo effect, competes against the ordering tendency. And this Kondo versus RCQY competition realizes the heavy fermion liquid can, and in the modern time, we realize that one could, strange metal is not too far away. And so here, it's a topology that dictates that real space orbitals must be hybridized in the right regime of correlations and in the natural regime of correlations. And this hybridization represents quantum fluctuations that's dictated by band topology. And that leads to a competition with the RQKY. So we adopted this scheme to show that in a model that is introduced to describe this setting, we can realize electronic order associated with a flat band and tune the hybridization to increase the hybridization to enhance quantum fluctuations to get a system out of electronic order. And there's various kind of scales which are borrowed from the heavy fermion experience, and realize a quantum critical regime that drives superconductivity. And we did numerical calculations to show that in the vicinity of electronic order, which is the analog of this curve, this cartoon curve, these are actually numerical data, and to show that there's a superconductivity, and TC is a few percent of the effective Fermi temperature as specified by the low energy physics, very much in the same spirit as how these scales are considered in the experiment, as I mentioned. So this the story about superconductivity in the twisted transition metal dichalcogenides is just the beginning, and I think there's a lot more to come experimentally, and a lot more to consider theoretically as well. But so at this point, I want to make the point that the bands in many ways are very clean. You know, we recently looked at the details of the Kagami metals. They're typically 30 bands that are mixed together, and it's a bit one has to work a bit harder to isolate in these realistic materials the molecular orbitals that is appropriate to describe these real space description and incorporate interaction effects. Here, the bands are much simpler, and there's a clear case to be made that electronic order is natural because of, in this case, half filling, but at least partial filling of a flat band. And yet, there's not only from this perspective, natural tendency for topological ordered typically insulating phases, but also for this kind quantum fluctuation regime that drives superconductivity. So it's almost like you have a sequence of you have a big parameter space in which some portions of parameter space realize something like fractional churn. You know, to really realize that it's a hard work theoretically as well. And then, but conceptually, in the other region of it, one has amplified quantum fluctuations and realize nominally high TC superconductivity. So that's all that I want to say. This work and overall direction has been a result of collaboration with many collaborators. I want to particularly highlight my student postdoc at Rice. Lei Chen just left his postdoc to Stony Brook, and Chen and Setai just moved to Iowa State to start a faculty job. And also long-term collaborations with some former student and postdocs, long-term theoretical collaboration with Kevin Ingersand, more recent collaboration with Jennifer Cano, my Recognieri, and long-term experimental collaboration with experimentalists from Silke Pasching's group in Vienna. So let me just wrap this up by reiterating that I've used two examples to illustrate point of what correlation can do for topology, and this is through these topological heavy fermion semimetals that leading to not just a highly renowned fermi liquid with
time difference between use and here.
with topology, but also new type of topological semimetals without quasiparticles. And conversely, I've addressed the question of what topology can do for correlation physics, and that is to through the Barry phase effects of the band topology leads to the dictates that there must be hybridization between the real space orbitals, and thereby inducing quantum fluctuations and leading to the competition with the flat band's natural tendency to order. And I argued that the recently observed superconductivity in twisted-WSe2 can be considered from this perspective. Thank you.
Yeah, thank you, Qimiao. Yeah, very nice talk. Any questions for Qimiao? Before anyone else asks, let me ask you for the case of the latest case. Do you think it's actually induced by? You said correlation induced by magnetism, or it's sort of there's no magnetism right in the system, or some sort
you
of
mean there's a twisted-WSe2?
Yeah.
Yeah. So the precise electronic order is interesting. Certainly, experimentally has not been fully clarified. It's not ferromagnetic order based on experiment. So
are there nearby?
There's also one aspect which I mentioned that the structure and energetic is such that there's a Valley spin locking. So it's a Valley degree freedom and spin degree freedom locked are mixed up in this system. So even if it's an antiferromagnet order, it's not conventional antiferromagnet order. Could show up.
I see. Okay.
That's an issue that is not clarified. In our calculation, we have this electronic order, and that's this real space orbital sitting on the triangular lattice, and there's a spin-spin interactions because that orbital is close to half filling. So in our calculation, this is antiferromagnetic order. But I think to interface with the what's going on with real material, there's still some time to be.
So there's no experimental evidence that there's any other sort of antiferromagnetic order or ferromagnetic order nearby, right?
I think the existing experiments, experimental studies of that correlated electronic order is not compatible with ferromagnetic order, is potentially compatible with antiferromagnetic order.
Okay. Yeah. So thank you, Qimiao. Yeah. Any other question for him? For Qimiao?
I might.
Yeah. Okay. Yeah. Okay. Go ahead.
Do you hear me?
Yes, I do.
Yeah, Henry. Yeah.
Yeah. Okay. I want to come back once more about the case that we have, which is the sodium cobaltate, in which we have absolute evidence that there is a flat band and which interacts with the broadband, and which gives things which looks exactly like heavy fermion Kondo lattices. And, nobody wants to see it.
I want to see it. I mean, I wonder whether this is an ideal system to study. In fact, if you look at this new Kagame material, let's see. It's on my slide. This cesium copper chromium 3 antimony 5. It's actually the superconductivity is happening under pressure, So I think the cobaltates that you mentioned, it would be good if there's some understanding of, say, RPES, see whether the flat band is there. And there's also the three-dimensional material, the pyrocore material, lithium, vanadium to oxygen 4. It seems like also will be opportune to, study the electronic structure and
you don't necessarily need RPES. It's difficult to do in that case because it's a 3D system, which is a lamellar system, and the surface cannot reproduce the bulk situation.
Yeah, cannot cleave. It has water in it.
I see.
Oh, yeah. even if you cleave, you are not going to get the order of the sodium at the surface, which yields the Kagome substrate.
Yeah.
So in the bulk, you see it, and in the transport, there is no problem. We see a band which disappears in field and temperature with a very large change of conductivity, and with a Hall effect which disappears in a very short increase of temperature or field. So it's obvious that we have something very narrow, and it's as it is an orbital Kagome structure. It's obvious that you will have the flat band. Well, we are not sure that we can use the single orbital Kagome to get the band structure that you show, but okay. Maybe some people will be able to do careful calculations to show that. I have not been successful in driving people to do that, but the experiments are beautiful. I'm sorry. This is the point that I want to show. The experiments are beautiful. They are published. They are free. Some of the effects have been seen 15 years ago, but the most recent are on the transport are only 3 or 4 years ago. But they are there, and they were extremely robust. Okay.
I agree with you. I mean, putting the other Kagome metals, the Kagome metals being studied, this is an example. There's a number of others, and the cobaltates and etc.
The advantage of the cobaltates is we know they are strongly correlated. And as we have effects which occur on short temperature, well, below 30 K. So we know that something, we have a very narrow band. Okay.
Yeah, let's move on. Yeah, I mean, what next question? Takamaka? Yeah, hello? How's that? Yeah, go ahead.
Hi, Qimiao. Thanks. Very stimulating talk. I wanted to understand a little better what you mean by topology-induced quantum fluctuation. So when we, in textbooks, when we understand quantum fluctuations, we have an ordered state in mind, which is destroyed, and we make some assumptions about the ordered state because quantum fluctuations intuitively we understand as two non-commuting operators, which are local operators. So starting from that textbook definition of quantum fluctuations, how should I understand what you mean by topology-induced quantum fluctuations which are agnostic to the ordered state?
Yeah, so the particular point I was making is actually very down to earth. In heavy fermions, when we think about quantum fluctuations, we think about getting out of the hard magnet regime of the phase diagram, and the way to do that is the Kondo effect, which is none other by the hybridization between the F and the C orbitals that is there due to quantum chemistry. Here, the analogy is that I have a flat band, and the chemical potential is only crossing this flat band. And so it seems to be very natural that this band diagonal physics, which I could also use some, I may not be able to use exponentially localized Wannian functions, but I could use some Wannian functions to describe in real space, and that very naturally have interactions that leads to electronic order. So you could also, if you want to be more general, can think about something like transverse field Ising model, where this is the Ising interaction that's diagonal, that promotes order. And now, due to the Berry phase, you cannot have exponential localized Wannier functions to describe this in real space, and you have to put these two bands together from linear superposition to go to the real space. So as a result, in real space, this topological obstruction dictates that there will be hybridization between the real space orbitals, and that hybridization is tuning. This is increasing this hybridization is tuning the system out of electronic order, very much like FC hybridization in the rare earth intermetallics. But I could also think more generally that this what this hybridization is doing is like the analog of the transverse field. It's the transverse part of the Hamiltonian that amounts to at least in the spaces amounts to quantum fluctuations. And in practice, it melts the order, and that in that sense, it is quantum fluctuation, and it's dictated by the band topology. If these were trivial bands, I could have interaction description in real space for this orbital or this one. Even if I want to put these two orbitals together, they don't need to hybridize with each other. And so in that case, the tendency towards when would it naturally be more naturally to be in the ordered part of the phase diagram, just because it's a half field or partial field or flat band.
I see. So is your theory only restricted to one Chern sector? Because there is, of course, the other Chern sector and the other valley that local interactions will mix the valleys. So
yeah, so that we can take care of. So as you form this combination, this construction, like these orbitals we've constructed, it has both valley, the information of both valleys.
Right. So is your superconductivity valley polarized, or is it the usual K and minus K formula?
No, it's in the spin sector, it's paramagnetic, and therefore it's not valley polarized. It's really in the paramagnetic portion of the phase diagram by both the spin and valley perspective. And we zoomed in to the quantum critical regime, guided in comparison with experiment, guided by the fact that the A coefficient, the T square coefficient of resistivity is varying by quite a bit, more than one order of magnitude.
I see. Thank you so much.
Yili?
Thank you very much. It's a very inspiring talk. I have a quick question following up with the previous one. So usually I heard that the fluctuation would induce like a residual Fermi-liquid interaction of heavy quasiparticles. So in this topology induced fluctuations, would that pick up the interaction or the residual Fermi-liquid interaction? Would that pick up some interesting form factors?
Yeah, so that's a very interesting and a very important question. So you can ask, if you have the linear superposition of the two orbitals, there's a unitary transformation that's being done, and so it should show up in form factors that should have consequences. And the precise consequence for both the normal state, the Fermi-liquid state, for the quantum criticality, and for superconductivity. I think all these are very interesting questions that still remains to be explored. So far, we've been content to at least go the first step to show that there is a superconducting instability, and TC is quite high from the perspective of this. I think the form factor is a problem that's waiting to be studied, at least from this perspective for this system.
Thank you very much. And also, if we look at the phase fluctuation, of the fluctuation, that gives rise some, I don't know, it's like dressed slave bosons or some pictures of that.
Yeah, so I'm not entirely sure which phase fluctuation, which phase you have in mind, but it certainly could, and one could even ask question, what's the nature of the order, whether in the ordered phase there's some interesting fluctuations that's attached to it. Again, it has not been looked at yet. It should.
Thank you so much.
Yeah, okay. All right. Yeah. If there's no more question, yeah. Thank you, Qimiao.
Yeah. Thank you, Benji.
Yeah, thank you, everyone.